This is the note video for slides 30 through 32 for section 1.6. 1.6 is a topic called continuity. So we're talking about the continuity of a function. So let's read here. It says a function f is continuous at x equals c if and only if the following three conditions are met. Number one, f of c is defined. In other words, we do not get an undefined value. So remember, undefined values would be 0 over 0, 1 over 0, infinity over infinity, infinity over 1, or like 1 over infinity. Any of those things are undefined. Okay? Now, next one, all right, the limit as x approaches c of f of x exists. So we may initially have plugged in and we got like 0 over 0, but then when we evaluate the limit, we get the function to, or the limit to exist. Well, that could mean that step 2, that condition is met. All right, but step 3, okay, it must be true that the limit as x approaches c of f of x equals f of c. So the only way that a function is to be considered continuous is if, number one, f of c is defined. Number two, the limit as x approaches c of f of x exists. And number three, those two things are equal. All right. Now, remember, this is a function is continuous at x equals c. So this is a point-by-point question. All right. So let's take a look at a graph. All right. Here is a graph of some function f of x. All right. Now, let's say that there is a particular value c here. All right. And we will highlight this. All right. Now, if we look at this picture, okay, is f of c defined? Yes, f of c is defined, right? Because there is a closed circle there, all right? The limit as x approaches c of f of x exists, meaning is the limit from the left equal to the limit from the right? Are they approaching the same y value? And the answer is yes. So are the limit and the value of the function equal? Well, yes, they are. So then I guess the question is when is a function not going to be continuous? Well, the easiest example to show is something like this, right? Well, let's say here's x equals c, all right? And then let's say that there's a y value m here, and then another y value, let's call that L here, all right? This is one that's very easy to see. The value of the function, f of c, is defined, but it happens to be L. And the limit as x approaches c is defined as well, but it happens to be m. Very clearly, L is not equal to m, and so this function is not continuous at x equals c, but it is continuous everywhere else. Think about it. Function limit equal, 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 function limit equal. So oftentimes we talk about a function being continuous on a particular domain of values, and then we generally say, like, well, maybe this function is not continuous at this one particular or two particular locations. All right, so that is the definition of continuity. Very important that we have this written correctly and we memorize it. All right, so now, okay, there are 4 types of discontinuity. Now, I just described the first one to you, all right? And so the first one here is one that we call removable discontinuity. Discontinuity. All right, removable discontinuity. Now, how would we recognize that we have removable discontinuity if we don't have the graph? Well, think about it. Number one, the function is defined, the limit is defined, but those two things are not equal, right? So we would say, like, number one is not equal to number two, right? That's a good way to remember like removable discontinuity. All right, the next one. All right, this is referred to as a jump discontinuity. All right, so take a look at this. We see that, well, the function is not defined, but what if it were? Well, let's say it was defined. Let's say it was there. Or what if it was here? Or what if it was here? It doesn't really matter. The jump discontinuity is still going to be present. So what does that mean? How would we recognize a jump discontinuity? Well, the limit from the left and the limit from the right are approaching different values. All right. So we could say like number 2 is different from the left and from the right. All right. All right. So that's number 2. We have removable, jump. All right. This one, there is a vertical asymptote. We refer to this as an infinite discontinuity. An infinite discontinuity. So what does that mean? Well, obviously we have this side is approaching an infinite value, and this side is also approaching an infinite value. Even if it were positive infinity, these are still approaching infinite values. So what does that mean? The limit does not exist. Okay, but it's a little different than number 2, where we had a jump discontinuity. So we do want to be able to distinguish between these. All right. And then the fourth one, all right, this is kind of an interesting one. This one is, it's called an oscillating discontinuity. Oscillating discontinuity. Number 4 is not very common. All right. 1, 2, and 3 are going to be much more common, but number 4 is still possible. So what's going on here? All right. This is actually the graph of the sine of 1 over x. All right, and so what's going on? Well, the function is not defined at x equals 0, nor is the limit. So f of 0. So let's say that sine of 1 over x is f of x. All right, what is the sine of 1 over 0? So that's saying the sine of 1 over 0. Well, 1 over 0 is undefined. So let's think about the limit. What is the limit as x approaches 0 of f of x? Well, that would be like saying the sine of 1 over 0, but in a limit problem, we accept that to be the sine of 1 over 0 is infinity, right? So what's the sine of infinity? Well, remember the graph of sine goes up and down and up and down and up and down forever to no end. So it is going back and forth between -1 and +1. It does not have a horizontal asymptote, right? If you think about what that question is asking. So this function is not continuous because this is an oscillating function. All right, but we say it's not continuous at x equals 0. Okay, so we would say like at x equals 0, but it is continuous everywhere else. This function is not continuous at x equals -2, but it is continuous everywhere else. This one is not continuous at x equals -2, but it is continuous everywhere else. And this one is not continuous at x equals -2, but it is continuous everywhere else. So that's the big key. It is continuous everywhere else. All right. Next, slide 32. All right. The intermediate value theorem. So it says if f is continuous, so obviously we have to make sure we understand what that word means, all right, on the closed interval a to b, all right, so we'll talk about that, and w is between f of a and f of b, then there is at least one c on a to b such that f of c equals w. All right, so that is one that we do want to memorize, but it's far more important that we understand what it means and we can apply what it means. All right, so intermediate value theorem. All right, so let's start here. We're going to draw a graph. All right, so we have A over here, we have B over here. Now, first step, if f is continuous on the closed interval a to b, so what does that mean? That means that we have an endpoint over here at a, and we have some other endpoint over here at b, and this graph goes between A and B without a hole, without an asymptote, without a jump, something like that. So basically, we have to have those 2 points connected without a whole asymptote or jump. Or I guess an oscillating part. All right. So anyway, so I'm going to draw this picture. Now, could the picture look like that? Yes, right? Because there's no asymptote, hole, or jump. Could the picture look like that? Could it just be like a line? Of course. Could the picture look like that? Now, I know sometimes people say, well, no, what graph would look like that? Well, we could have like a piecewise graph that would look like this. But the fact is that if there are no holes, asymptotes, or jumps, then the graph is valid. So basically, I'm going to draw the simplest graph, and that's just kind of like a line. All right. So now let's continue. It says, and W is between f of A and f of B. All right, well, what is f of A? That's the y value here. What is f of B? That's the y value here. All right, W is some y value in between f of A and f of B. All right, then there exists at least one C on A to B. So what does that mean? That C is an x value happening somewhere between A and B. So C is right here. Okay. W is between f of A and f of B, then there exists at least one C on A to B such that f of C equals W. So f of C meaning what? The value of the function at C is equal to W. So what we're saying is that if you go from A to B with a continuous function, then there must be an x value everywhere between A and B that is going to lead to a y value everywhere between f of A and f of B. In other words, if I start here and I start here, I have to go through each and every y value in between f of A and f of B. And there must be a corresponding x value that gives you that y value. So that's the intermediate value theorem.